I've seen some art, it's like, it's embarrassing, but at the same time, you have to accept your opinion. It's always funny. When they read, it's like, ooh, don't be in that chapter. You're going to be stuck in that.
Y'all prepared.
You're stuck there for like, it's only 2 in the morning. You're right at the Alamo area, you're about to stump.
Uh-oh. What happened? You all right? Sprain, okay. All right. So I wanted to start class with a kind of a group activity. So let's do this. Let's make sure that you're paired up at least 3 people. No more than 4. Minimum of 3, maximum of 4. Now, let's say minimum of 2. All right, we'll say minimum, but the more brain power, the better. Now, I'm not sure how this is going to work. Okay? Y'all ready? I'm going to somehow count this as a bonus, but it's going to be based upon which group or groups get this, all right? So your group has to get to some, not solution, but some at least approach to this. And so I want you to talk quietly amongst yourselves, all right? I don't want you all sharing with the other groups. The volume of a solid ball if you open up a textbook, is 4/3 pi r cubed. That's the formula. So if you know the radius of the ball, you know its volume. I want you to think about what we did last class and how it is that you might go about verifying that that formula is true. Like, how could you come up with that formula yourself? All right, I'm going to give you maybe 8 minutes to talk amongst yourselves. And I'm not really going to give you anything other than that. Just see what you can come up with in 8 minutes. Okay? Keep it to yourselves. And Googling volume of sphere is not an answer as to how you could come up with a formula. How could you use what we did last class? Look at what we did at the end of class last time. We're working in groups. You might want to just pull up over here after you put your bag down. That group, no, that's fine. I told them to work in a group and try and figure out if they could come up with a way that you could show that the volume of a sphere, a solid ball, is 4/3 pi r cubed, using what we did at the end of class last time. Okay. All right, here's what I want. At this point, I just want to talk, all right? So I need at least one person from each group to be their representative to speak for the group. So decide who that's going to be. Everybody have a representative? Okay. Here we go. All right? Let's see how this goes. All I want is a verbal explanation of what your group thought you could do to come up and verify that formula is true. All right? And we got to start somewhere. So any volunteers to volunteer their idea first?
We were just talking about.
Okay, hold on. We got who's your spokesperson? All right.
So you were thinking that you would take the antiderivative from 0 to pi because the half circle is basically half of the sine term, or at least like from 0 to pi.
Okay, so you're saying that.
It's basically a sine graph, and then you rotate it over the.
So your idea is that take the sine curve. Is that what you're saying? Take the sine curve? And then go from 0 to pi. Okay? And then rotate this around and you would get something that looks like that. Okay. Good enough for now. All right? What other group was going to volunteer?
Well, we were trying to figure out like a half circle and then rotate around the X.
So take a half circle.
Yeah, and then he came in and suggested a cosine function, and then trying to figure out how to make y equal to like another like y equal to 0, and then the area from cosine to the.
So you got two different things. You had take a half circle and then rotate that around the x-axis.
Yeah.
Or you said like take the cosine curve, which goes like this and goes that way also.
Yeah, I'm trying to figure out like only to use from.
Like here to here and rotate that?
Right.
Okay. What do you got?
So what we're thinking is kind of instead of drawing a rectangle since it's a volume, we're thinking of drawing a circle.
Mm-hmm.
Kind of moving it up and down, I guess adding those, kind of like how we did with the rectangles where you add them up. But
Yeah.
Without using a formula. Something similar to that, but we couldn't really go further. We
Yeah.
got stuck like.
Okay, so you were thinking you need a Riemann sum, you need some way of adding up a bunch of circles that keep on changing radius, right? Okay. So we got 1, 2, 3. Go ahead. What do you got over here?
You just drew half a circle
You drew half a circle.
on the graph.
Okay.
Starting from the X.
Oh, you mean starting from the origin, like here to here, like that? Okay.
And the height was r.
So the height of this circle was r.
And like the whole entire diameter is 2r.
So this would be 2r. Okay. And what are you going to do with that half circle?
Well, we were gonna use this, what's this called? The cone, the volume one.
The cone volume one? Oh, like we did last time. Uh-huh. Yeah, yeah.
I used that one.
Okay, so did you actually come up with what this curve was, or no?
No.
Never. Okay, but your idea is that you're going to wrap this around the x-axis? I think this idea and this idea are pretty much the same idea.
Yeah.
Half circle wrapped around the x-axis. Yeah? Okay, good. You didn't compute anything, right? Y'all didn't actually like get an answer, no? I thought you said you got it. No? I thought you said, I thought I heard you say you got 4/3 pi r cubed.
Got it, but like, I don't know.
Okay. Okay, I'll have to look at it. All right, did we ready to talk? No?
Oh, we kind of had like, try to like, I guess, piece it together like they were trying to do.
Mm-hmm.
With, another formula.
Okay.
Couldn't really like figure out which way to start it, I guess.
Okay.
Yeah.
So were you thinking at all about wrapping something around the x-axis, or?
We were thinking of the, not the half circle, but kind of like the sign over there.
Okay, like the sign?
Yeah.
Okay. Who's left? Just, okay, what were you all thinking?
So we had the idea of taking the first half of the circumference from the origin till D, so the 2R, and then
So like this again, or no?
yeah, so the
Same picture?
But then we were still having trouble targeting how you would set up the area. So.
Okay. All right. So this was just really an exercise to see like how far you could get with this idea just off of what I gave you last class. Because first thing I wanted to do today was come in here and prove that this formula is actually 4/3 pi r cubed. So I just thought maybe if I gave it to you, you might kind of at least mentally start to think, okay, what we could do to create a sphere is take some function, wrap it around the x-axis, and create the sphere, right? That's last class, that's what we talked about. We talked about if we had two functions. In fact, this is what we had. This is a more formal explanation from last class. We said that if we had a function, or two functions, and we looked at the region between the two functions, and we wanted to take this and wrap it around the x-axis, that we would look at this rectangle, bring it over here, imagine wrapping that around the x-axis, and it would have created this, we called that a washer, didn't we? It would create this washer, and then we said, well, that washer, the volume of that washer is the volume of the solid washer, which we could call a disk, right? This is more like a disk, not a washer. with taking this part out, the blue part out of the middle. And then we came up with formulas for each one of those. Okay, that's what we did at the end of class, right? And we said that the volume of that solid would be pi times the integral from a to b of the top function squared minus the bottom function squared, right? Okay. So with that, let's address each of these. There's really maybe 2 or 3 concepts here that look like you were on your way. Let's address the sine one first. Okay, so if you take the sine curve and you just go from here to here and wrap that around the x-axis, that is not going to be a sphere. It's going to look like a sphere, but it'll be more like a football than it is a sphere. And here's how you can tell. What's the distance from here to here? That's pi, right? But what's the distance from here to here? 1, right? So you have, this would be the diameter of the sphere, would be pi, but then this radius would be 1. And so you see that wouldn't create a perfectly shaped sphere. Understand? Now the idea is right. We want to take some function and wrap it around the x-axis, but that one's not going to work. The cosine one will also not work for the same reason. Okay? So then we get to the half circle, right? So the half circle, this was a good approach. We have the radius is, if the radius is r, the distance from here to here is r, and the distance from here to here is 2r, that will work. The question is, what's that curve? Like, what's that actual function? Right? Because what we needed from the notes is that you needed to have, a top function and then some bottom function, g, right? We needed a top and a bottom. But we needed to be able to express that function as a function of x. And so you would need to somehow represent that half circle as a function of x. Am I making sense? Okay, so this will work, but what's that? Another approach was to take the half circle, and I don't know if anyone told me to do this, but another approach would be like, this is r, that's negative r. It's basically this picture just centered at the origin, right? Do y'all agree? And wrap that around the x-axis. But we still come in with the same question, like what's that function, right? Understand? Okay. Well, we actually did this problem. Do you remember when I showed you the area of a circle is pi r squared? Do you remember that problem? Okay, when we did that, I did the same thing. I said, look, if we just take the top half of the circle and take the equation of that circle and solve for y, we will have it as a function of x. So that's what I'm about to do. All right. So I think a lot of you were on the right track. All right. It was just an exercise in you trying to visualize what's happening. All right. So let's actually do this. Let's prove that the volume of a solid ball with radius r is 4/3 pi r cubed. And I think you're going to really enjoy the fact that this integral is not hard at all. All right, so let's do this. First of all, let's start with a picture. And let's start with a circle centered at the origin with the radius of r. What is the equation of that circle? What's the equation of that circle in terms of x and y and r? X squared plus y squared equals r squared. Y'all need to get that pretty much burned into the brain at this. I mean, at this point, as Cal 2 students, you should know what the equation of a circle centered at the origin is. That's what it is. All right? So if I take this and solve it for y, which we have done in the past, we get plus or minus the square root of r squared minus x squared. And that's just moving the x squared over and then taking the square root. We get plus or minus. And so we actually have two curves here, don't we? We have a positive root, which actually gives us the top of the curve, and we have a negative root, which gives us the bottom of the curve, or the circle. All right? To do this problem, what I'm going to see if you agree with me on this, what if we just look at that piece right there? If I take that piece right there and wrap it around the x-axis, I would get half half of the sphere, or half of the ball, wouldn't I? So that's what I'm going to do. Now, since I'm dealing with the top half, right, I know that I'm dealing with the positive root here. So this right here is y equals square root of r squared minus x squared. We agree? Now, I want to wrap that around the x-axis. I'm actually going to draw my picture again because I've got too much stuff over there. So I'm going to draw it again. Taking this curve right here. It goes to r here, right? That's where it goes. And then up here is r also. Not that that matters, but that is r both ways, right? So I imagine taking rectangles in here. And notice that my rectangles go all the way to the x-axis, don't they? I'm going to be wrapping these around the x-axis. So what is the bottom function then? I mean, if the top function is that blue function, then what's my bottom function? It's the x-axis, right? Which has the equation y equals 0. And the top function has the equation y equals the square root of r squared minus x squared. All right? So I'm going to come over here to the side. I'm going to draw my little arbitrary rectangle because this is kind of the standard approach I use for all these problems. I say I'm going to take that piece and I'm going to wrap it around this axis, right? The top function is always the blue one, and the top one I've always called f, haven't I? So I'm going to say f of x is the square root of r squared minus x squared. And the bottom function is always the red one, right? Which is, well, g of x, right? That's what we called it. And that's the constant 0 function. And according to last class, the big thing that we ended with was that if you take any region where f is on top and g is on the bottom, and you wrap it around the x-axis, that the volume is equal to pi times the integral from a to b of the f function squared, right, minus the g function squared dx. That was the major result from last class. I know it was at the very end, but it was a pretty major result. So look at this. For this problem, do we have everything we need to do this formula? Yes, we have everything, right? I start out, I know the volume then, when I wrap that around the x-axis, the volume will be equal to pi. Now what's my integral going to go from? 0 to r. So because we're integrating with respect to x, my rectangles are moving this way, right? Like left and right, which means we need a left endpoint where we're going to start, which is 0, and we're going to end at r. And then, this is the great part. This is the part that makes this problem so nice. What am I going to do? I'm going to take the f function and square it. And that gets rid of the root, right? Now, when we did the area, right? I proved that the area of a circle is pi r squared. When we did the area, the formula for area, the only difference between this and the formula for area is that that's not squared, and pi's not there, right? If I take the pi out and I take the squareds off, it's the area between the curves. Pardon? What?
Why is it squared?
You have to go back to last class. Is when we came up with the formula using the volume of a cylinder. It was pi r squared times height, and we used that formula to create this formula. So check this out. When we did area, we did not get to square that, did we? And then we had to use trigonometric substitution to do the integral. But here, because we get to square it, it just becomes r squared minus x squared. Isn't that nice? And then minus what? Minus 0 squared. So that's it. That's all we have to integrate right there. R squared minus x squared. And remember that r is a constant, right? R is a constant. So this will become pi times, let's get the antiderivative. The antiderivative of r squared is antiderivative? Oh, careful, r is a constant. So that, nope, you're going the wrong way. So look, imagine that that's the number 4. The antiderivative 4 would be 4x, right? R squared x. Okay, that's the antiderivative of r squared. Now minus, See, now this is 1/3 x cubed, right? Because x is our variable. So we've got 1/3 x cubed. That's our antiderivative. Now we come in with that evaluation bar. We're going from 0 to r, aren't we? Okay, let's start plugging things in. We are going to replace x with r first, then x with 0. Okay, let's replace x with r first. When we do that, so at this point we're going to have something in parentheses minus something in parentheses, right? So when r goes in here, I've got my pi out front. I've got r what? R cubed, because that's going to be an r. So r cubed minus 1/3 what? R cubed again, because I replaced the x with r. And then minus, that should be another set of parentheses there. So it's pi times all of that, right? Yeah. Then minus, what happens when I plug in 0 for x here and here? It's all gone, 0, right? So what's 1 r cubed minus 1/3 r cubed? That's 2/3 r cubed, isn't it? Right? 1 minus 1/3 is 2/3. Those are like terms, r cubed, r cubed. And that's 2/3 pi r cubed, right? Yeah, remember that was only half of it, right? That was only half. So if that was me wrapping this around, it gives me half of the volume. So if I double this, multiply that by 2, what do you get? 4/3 pi r cubed. That's it. Look at that. You can prove, with the formula that we developed at the end of last class, you can prove that the volume of a sphere, or a solid ball, is 4/3 pi r cubed by simply knowing how to integrate using power rule. Like if you can do power rule, you're done, right? So it's actually easier to do this integral than it is to do the area. That's just the way it works out. Okay. So I think a lot of you are on the right track. The point here, the thing I want you to really take away is once you have the idea of what you need to do, then you actually have to come up and actually define these functions. Then you can use the calculus. Understand? There is a formula in the book. There is a formula, well, in most books, right? You can find the formula for the volume of a cone. What is, if somebody gives you a cone, okay, like this, a right cone, and you know its height, and what else do they probably give you the radius. Then does anybody know what the volume of that is? It's probably in the front or the back of your book in your formula sheets. It's 1/3 pi r squared times h. Okay? Now, if I take the 1/3 out of here, then that formula is the formula for the volume of a cylinder. Look, if I were to take this up like this, sorry, that cone's supposed to be right in the center, but you get the idea? Yeah. Okay? So if you just look at pi r squared h, that's the volume of the blue part. A cone is 1/3 of it. Does it make sense that it would be that? It kind of does make sense that it would be that, right? How could you show that, though? How could you show that the volume of a cone is 1/3? I just want us to think about it. I'm not going to work this all through. How can you look at this cone as something wrapped around the x-axis? What object is that wrapped around the x-axis? It's a line. It's a line. Look, if I come here, go like this, and I draw a line like this, from there to there, and I wrap that around the x-axis, I have a cone, don't I? So what you need to do is come up with the equation of this line. Agreed? How would you come up with the equation of that line? Well, do you know what this point is? Come on, you know what it is. What is it? It's 0, I heard it, r. Isn't that the radius? Isn't that the distance from here to here? Right? And what's this point? H, 0, right? Isn't it? Can you tell me the equation of a line if I give you 2 points?
Yes.
How? Yeah, you use this formula, y minus y1 equals m times x minus x1. Remember that equation for, it's called this, we call this the point slope formula for a line? Okay, so let's pick this right here to be our x1, y1. Let's pick this to be our x2, y2. So I know y1 is going to be r, right? And I know x1 is going to be 0. I just need the slope. What's the slope of the line between those? Or what is the slope? Yeah, slope of the line between those 2 points. y2 minus y1, so m is y2 minus y1 over x2 minus x1. So what's that? Negative r over h. Agreed? Okay, so according to this, y minus r equals negative r over h, x minus 0 is x. So y is equal to negative r over h, x plus r. This is the equation of that line. Now remember, r and h are constants, right? The radius is given, the height is given. So this is the equation that we could integrate. Now, are y'all following this? Yes. Okay, so look, I guess I am going to take it all the way. Negative r over hx plus r, right? That's what that is?
Yeah.
Okay, that's my top function.
The bottom function.
Bottom function is what? Y equals 0. Again, right?
Yeah.
Okay, so I already know right now that I'm going to do pi integral from 0 to h of the top function squared minus the bottom function squared, but the bottom function is 0, right? So isn't the volume of that pi integral 0 to h top function squared? I'm going to go ahead and just put it negative r over h x plus r squared minus 0, right? Dx. Okay. I said I was going to take it all the way. I don't think I've ever proven this formula. Pi integral, I'm not going to integrate yet. Let's expand this. This is something squared, right? So let's just multiply it times itself. Okay, so when we do this time, you know what I'm doing, right? Like this, FOIL? Okay, so I get r squared over h squared x squared. Then what?
And then
Negative r squared over h x, but then another one, right? So negative 2r squared over h x. And then the last one, plus r squared dx, right? Integrate this with respect to x now. So this is going to be pi. Okay, antiderivative of this with respect to x, 1/3, right? This is a constant. So how about I write it this way? R squared over 3h squared, x cubed. So here's my 1/3 right there. Now this one minus, I'm going to get a 1/2, right? That 1/2 is going to kill the 2. So I'm just going to get r squared over h x squared. And then this is a constant, so r squared x. Evaluating this from 0 to h. Agree? Okay. Well, let's just take care of the 0 first. When I plug 0 in, everything's dead, right? So all that really matters is what I get when I plug h into this. So let's plug h in. And we'll have pi integral, what am I saying? Plugging in h right here, right? So this is an h right here. H cubed over h squared. I'm going to have 1h remaining, yes? So I'm going to have r squared over 3, and then I had that 1h left, right? When I plug in h squared here, I have 1h left, so minus r squared h. And then when I plug in h here, I get plus r squared h. Ooh. And these cancel. So I'm left with this, which if you rewrite it is 1/3 pi r squared h. You could go all day with formulas like this. What if we wanted to find the volume of what's called a frustrum, which is a cone with some part of it cut off, right? So what you could do is just simply adapt the formula a little bit, right? You just, you go like here to here, right? But you would have to change, like this would still be r, right? But normally when we do this, we give you like an R1, which is the base here, and then they give you an R2, which is the radius up there. And then you come up with a formula. So what would happen is in our picture, this point would be 0, R1, but this point would be what? Oh, we'd have to have the h also. Sorry, we would have to have this h. So h would be given to us. So we would have, this would be HR2 instead. And then you do the same exact thing. You come up with the equation of the line, blah, 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 blah. Okay, so any geometric shape that has some symmetry to it that you could create by rotating something around the x-axis, you can generate a formula for it. That make sense? Okay. Very powerful stuff we've got here, this tool. All right, with all that said, let's do a quick review. All right, just a quick review of what we have so far. We have this. Two functions, f on top, g on the bottom, going between a and b, right? Then if we want the area, what's the area of that? Integral a to b, f of x minus g of x dx, right? That's it right there. That'll give us the area of that region right there. Okay? Now, what if I ask you to take that and wrap it around the x-axis? Now watch what I do here. I draw like a little half, like a circled arrow, and then another one like that. And that gives the impression that you're rotating it around the x-axis. Do y'all see that? Okay, so how do I get the volume of that? I'm going to say the volume about the x-axis. So I'm rotating it around the x-axis. What's the volume of that? Yeah. Pi integral a to b, f of x, that thing squared, and then minus g of x squared dx, right? And I could just do that. There we go. But you square them separately, right? You square them separately from one another. You always have to have pi there. Yes. Yep. Okay, that good? Now, what if we do this instead? What if your functions are not functions of x, but instead they are functions of y? So let's call this function over here f of y. That's this one. And then the one on the bottom here. It's not the bottom, it's left and right. We talked about that last class, right? That when you want to do this region and these are not functions of x, you kind of have to turn your head sideways and imagine your rectangles are going to go in this way, right? I should have put my rectangles in here this way, like that. Okay, so when we do this, they're functions of y instead of functions of x. The function on the right goes first, and then the function on the left goes second. So what would be the area of that thing? Integral c to d, right? And those are going to be y values, aren't they? Okay, and then it'll be f of y minus g of y dy. Now, we haven't discussed this, but one of the great things in mathematics is that a lot of things that we do, we can, they say, what they use in math is this thing, without loss of generality. That's what that means, without loss of generality. So if we understand how this came about and how we created this formula, right, then we should have a volume formula for this one too, if we rotate it around the y-axis, right? Like if we go and wrap this thing around the y-axis, like this, then the volume of that should be, if there's any justice in the world, right, which there's not, so what should it be? Pi integral c to d, the f of y squared minus g of y squared dy, right? dy. And that is true. That is exactly what it would be. Because all you're doing is you're creating washers that go this way instead, right? Instead of your washers going that way, your washers go this way. So if you were to draw one of those washers, just so you can see it, if you drew one of those washers, right, then how tall is it? dy. So that was this, right? And then what we did is we looked at what would the volume of this whole thing be without the center cut out, right? That would be, well, we need to know that distance, right? And what's that distance? That's the distance from the y-axis to here, right? So that would be f of y. So the formula for this, the volume is pi r squared times the height. There's your height. The radius is f of y. So is this okay? You sure there's no questions on that, on this? Now, here's more of a theoretical question for you. Let's say I give you the region between two curves. Okay? I give you some arbitrary region between two curves. Like this. Whatever. There it is. And let's just call that region R, all right? If I wrap that around the x-axis, it's going to have a volume, isn't it? If I wrap it around the y-axis, it's going to have a volume. Are they the same volumes? What do you think? Yes? No? Any objections? Imagine wrapping that around the x-axis, you'd have a volume. Wrap it around the y-axis, you would have a volume. Are they always going to be the same volumes? Let's take a vote. How many of you think that they will be the same volume both ways? Okay. How many of you think that they will not be the same volume both ways? Okay. Well, how could we convince ourselves? We could do an example and do it both ways, right? But what if they both came out to be, that's an interesting approach. What if we're trying to figure out, is it the same both ways, right? So what if we do an example and it turns out to be the same both ways? Is that enough to prove that it's always that way? No, right? That we just could have just picked one that worked, right? So in mathematics, if you're trying to prove something, it's very hard to prove something is true all the time. It's easier to show that it's not true or true sometimes, because all you'd have to do is one example that didn't work, right? Can we come up? Okay, so I'm going to spoiler alert here. It's not the same both ways. Sometimes it is, sometimes it isn't. Like if we take that, remember that piece right here that we proved the formula for the volume of a sphere or volume of a ball? If I wrap that around the x-axis, it's going to be identical to wrapping it around the y-axis. Identical. So let me give you a very simple explanation, or not simple explanation, a simple example. What if I just take that rectangle right there? Okay? And I wrap it around the x-axis. What's it going to look like? That's what it'll look like, right? And that'll have a certain volume. What if I wrap that around the y-axis? What's it going to look like? It's going to look like going to look like that, right? Right, my y-axis is right here. Which of these has more volume? Well, okay, you could maybe argue with me, oh, they're the same, and maybe there's a way I can make it the same. But what if I took this and just slid it way out here, right? Is that changing at all? If I move this rectangle out to the side, is it changing at all the volume of it wrapped around the x-axis? No. No. Is the volume around the y-axis changing? Yes. Absolutely, because it's got to go all the way around, right? And so I'm going to have a huge solid object that has a lot of volume to it. So in general, wrapping around the x and the y give you two different results. Just depends on the actual function. We good? All right. It depends on, at this point, because we're only talking about wrapping around the x and y axis, it would depend on the geometric shape that we're revolving to begin with. I mean, that's what would dictate it. But in general, it's not the same. So if you're asked to find the volume wrapping it this way and volume wrapping it this way, expect two different results. All right. Are you all ready? Okay. Let's go back to this picture again. F is on top, G is on the bottom. We're going to go from A to B. We just wrote down the formula for wrapping this around the x-axis, right? Yeah? And we're all comfortable with that, it appears.
So area would be the same though, right?
The area is the same. Yeah, because we're not wrapping anything around anything. When we say the area of that, it's only one thing. All right, so what I'd like to do now is I wish there was a ruler in here. There's not. So I'll just use this. When I wrap this thing around the x-axis, right? When I wrap that around the x-axis, would you agree with me that that solid, I don't know, the top of that solid and the bottom of the solid is about like this big, right? The top of it. Like if I could bring it off the paper, hold it, right? That's about how big it would be? Because the distance from the axis of rotation to the top edge is that far. So I should have that same distance this way, yes? Okay, so what if I do this though? What if I, instead of asking you to wrap this around the x-axis, I ask you to wrap it around some arbitrary line down here? It's just gotten bigger, hasn't it? Yeah. I mean, because when I wrap it around this axis, it's going to be about that big. But when I wrap it around this axis, look, swings out way down here. Now that thing's about that big, right? Different volume then, isn't it? Yeah. Much different volume. Well, I wonder if we can come up with a way of determining what that would be. Of course we can. All right, so let's do it. So we are going to wrap this around the x-axis. Ready? Or not, sorry, we're not wrapping around the x-axis. We're absolutely not wrapping it around the x-axis. We're wrapping it around this arbitrary line. And that line, I don't know, let's just call it y equals some constant k. Because isn't that the way we define horizontal lines? Yeah. Y equals a constant? Now in this case, it looks like k would be negative, right? Because it's below the x-axis. But I'm more concerned about how would we come up with a formula for this. So I'm going to move over to the side. I'm going to draw the x-axis, which I've done in the past, right? So here's my little x-axis. I'm going to draw over to the side my axis of rotation, which is my y equals k, right? And then I'm also going to do what I've done before, and I'm going to take that little rectangle in here, and I'm going to bring it out over here. And I told you, let's continue to do that because later on we might find it useful. And I'm hoping this is the point at which you're going to see that. When I take this and wrap it around here, right, I get this huge washer, don't I? So I'm going to draw that to the side here. And it doesn't have to be drawn to scale or anything. It doesn't have to look perfect. It's more that you understand kind of what this looks like. Okay, so it's got like this thickness here. It goes all the way around this line, comes back around, and so you've got this huge like hole in the middle, right? I could like jump through this thing. Yes? Okay. What is the volume of this? Well, remember before, what we were doing was we were saying when we have a washer with a hole in it, we looked at it as being the washer without the hole minus the washer with the hole, like that right there? Okay. And to do that, we said, look, this washer, what was the radius of this washer? It was f of x, right? And what was the radius of this washer? G of x, right? Are y'all sure? Yes? So what we're most concerned with in the formula is the radius of the disc washer-ish thing, right? The radius, which is the distance from the center to the edge, which for us is the distance from the axis of rotation to the top edge. Agreed? So if I know that the distance from here to here is f, and I know the distance from here to here is the absolute value of k, right? Then wouldn't the radius of this big washer, disky thing looking thing, wouldn't it be f plus that? Wouldn't it be? That would be the radius. So it's kind of like, instead of using f of x squared, it's actually, how do we say this? Yeah, so how about I try and create a new formula for you using some words that might help you, all right? So our new formula for this is the volume is going to be, well, same thing, pi is still here. We're still going to integrate from a to b because we're still moving our rectangle from left to right. But now, instead of saying f of x squared, I'm going to say this, and let's see if you understand this. Capital R out, subscript out. What does that mean to you? The radius of the outer edge, right? So it's like the way you measure this is you imagine yourself, I always try and imagine myself standing at the axis of rotation, like a person. Okay, this is my top of my head, my feet are on the ground. I'm looking out and I'm trying to figure out the distance from me to the outer edge of this rectangle. That distance, in this particular problem, it's f plus k, right? But every problem we do from here on out, it's going to be different. It depends on where you're standing. Because what if my axis of rotation was up here? Then I have to measure something different. So I just want you to look at it as the outer radius from you to the outside of the rectangle, okay? So this right here, whatever it is, this distance from here to here is r out. Okay, and I'm missing something on that, what? Squared. Okay, so this radius thing squared. And then minus what? R in. Okay, so the radius on the inner squared, and that in my picture is the distance from the axis of rotation where? To the bottom edge of the rectangle. That's my R in. My inner radius squared, and then all of that, what? D. Well, in this particular setup, what would it be? D what? Dx, but it could be dy if we are turning ourselves the other way, right? So this is going to be d, who knows, okay? It depends on which way we're facing. I know this looks weird, but for us in this class, it's either going to be x or y, all right? See, the big thing I'm trying to get you to understand here is that, I mean, this is a formula, but really it's more about understanding like where it's coming from the picture. That's more important than like, you know, what's the formula? Just give me the formula so I can compute, you know? Like understand how this comes from the picture. All right, let's do an example. We're starting to get to problems that are going to start looking very similar to what you'll see on a test. And we're going to start with a function I think that'll be easy for us to draw and easy for us to do what we need to do. All right? So here we go. Let y be equal to x squared and y be equal to x. Yeah, that's very clean. Okay, part A. Find area of region bounded by curves. Part B. Find volume if region is rotated about the x-axis. Part C. Find volume if rotated about y-axis. Okay? So we've got these curves, we've got a region that they enclose. We're going to find its area. We're going to rotate it around the x-axis, find its volume. We're going to rotate it around the y-axis, find its volume. We're not done though. Find the volume, rotated about y equals 5. Where's y equals 5? Up, okay? All right, part E. Find volume, rotate. Notice I'm getting shorter and shorter with my language here. Rotate about y equals -2. Yeah, so this is like what a test question would be, but for what I would tell you, what I'm missing here in the test question would be set up the following integrals but do not evaluate them. Okay? Set them up. So you have to get the correct setup of the integral and then you move on. You don't have to actually run through and do the integration. Okay? So it's all about you got to get the picture right and you got to know how to create the formulas. All right, ready? So we have x-axis, y-axis, y equals 5, y equals -2, and then of course the area. Let's take care of part A first. Part A, set up the integral. Well, should we draw a picture? Yeah, we should draw a picture. Let's draw a picture over here. X squared. There's x squared. Okay, and y equals x. Like that. Right? All right, so I think from this picture, I hope from this picture you can easily tell which function is on top and which function is on bottom, right? So what would the area be? Oh, well, do we know where they hit each other? I kind of skipped that. I thought it was too easy. In this particular problem, they hit each other at 1, 1. I mean, let's just set that equal to that. If I set x equal to x squared, how do you solve that equation? How do I solve that equation? Okay, so I'm hearing two things. Divide by x and move everything to one side. Which one? Does it matter? It absolutely matters. Now watch, if I divide both sides by x, what do I get?